Hello, this is Alex. I'm a data scientist at Mayo Clinic in Jacksonville. This is a follow-up to the previous video where I showed you how we can use a deep learning model to automatically segment anatomy in the pelvis from a CT scan. In this video, I'll be showing you how we can use RIL-Contour's ROI statistics tool to generate meaningful metrics from this segmentation. So in the previous video, we put a lot of hard work into generating this beautiful segmentation. So fat in green, muscle in red, bone in light blue, and now we can see how we can get some meaningful numbers from this. So to do that, we'll go up to Window, ROI Statistics. This can take a second to compute because RIL-Contour is actually calculating this on the fly. So it'll start with the ROI that you have selected, which in this case is muscle. You have the choice between the slice that is selected or the entire volume. We'll stick with volume. First, we have intensity measurements, so the mean Hounsfield unit value, standard deviation, median, and the voxel count. We also have volume, which is probably more what we're interested in. So we have the total volume of the muscle compartment in millimeters cubed. This is based off the voxel dimensions, which are in real units. We also have the largest slice area, the location of the largest slice, and the diameter or the single longest distance for the largest slice. Finally, we have the histogram here, which shows our peak just below Hounsfield level 0, which is about what we would expect for muscle. We can do the same thing for any compartment, so we'll select fat, Window, ROI Statistics. For this one, we see the mean Hounsfield unit value is more negative, which is expected because fat is less dense than muscle. We have the volume here as well. And finally, our histogram shows a more distributed peak and a more negative peak. So this is how we generate these statistics for a single volume. You can also do the same thing for the entire project. So typically what I'll do for a project is you'll do all your segmentations first, and then once you're done, you can generate statistics once at the end. So we'll go to File, Export, Project Voxel Annotations, not the most intuitive name. Select the ones that you want. Leave this checked. Export. It's going to ask you where you want to save it. We'll save it to the desktop. I can type. Okay, once again, takes a few seconds to compute, but now if we minimize the window, you can see that RIL-Contour has exported the scan we were working on, as well as one other scan that I had segmented. And it's a pretty complete export. So here's all of the ROI statistics that we talked about in the pop-up menu, as well as information on the orientation, scan volume. I believe there's also. So finally, I thought it would be interesting to end this video by talking about what some of these metrics mean in the context of body composition. So I've gone ahead and done a summary of these metrics for this patient specifically. So I've taken fat, muscle, bone, and organ. And from that ROI statistics menu, I calculated the volume in centimeters cubed, the percentage, the mean Hounsfield unit density, and the standard deviation. So we can actually tell some pretty interesting things from this patient based on our segmentation. For example, we can compute that they have 43% fat by volume, 38% muscle, 9% bone. So you can infer that some of these metrics might change, for example, if the patient has sarcopenia or frailty. Finally, we can look at the Hounsfield unit values. So for fat, this is pretty much constant. In muscle, this is more interesting. So what we see is that the density of muscle tends to decrease in older patients and in frail patients. This is due to two things. Firstly, the intramuscular fat that I showed in the previous video. So you can see that there's actually fat in between these muscles. These fat pads tend to increase in frail patients. But it actually also reflects intracellular fat as well. So sometimes in frail patients, the muscle cells themselves will have more adipose deposits in them, which is also related to frailty. We also see an increase in the standard deviation in muscle in frail patients, which reflects the more heterogeneous appearance as these fat pads begin to replace the muscle. Finally, for bone, we can look at osteoporosis, not just in the bone volume, but in the density. You can imagine that bone density is going to decrease as a patient has osteoporosis. So hopefully this gives you an insight into some of the things that we're interested in with body composition, why we're using RIL-Contour for this project. So we're looking at the impact of body composition in several different projects. It's particularly important for pancreatic cancer. So we see pretty dramatic changes in body composition in patients just before they're diagnosed with pancreatic cancer. We're also looking at bladder cancer. And finally, the purpose of this project, which is knee replacement. So we're seeing if frailty and osteoporosis has an impact on how a patient recovers from knee replacement. So of course, the promise of AI is that we can do these segmentations automatically. Rather than doing the manual corrections ourselves, we can just run the algorithm on dozens or hundreds of scans at a time, generating not only population metrics, but patient-specific metrics that we can use to better tailor our treatments to our patients. Thank you so much for watching. If this is something that you're interested in with your own research, I hope you reach out. More than happy to collaborate on these types of body composition studies. Thank you very much.